Hiya, it's Mr. Baker here, and today we're going to be looking at specific latent heat and internal energy. So today we're going to be looking at internal energy and specific latent heat, and really we're going to be trying to answer this question. When you heat things up, why do they sometimes get hotter but sometimes change state? Like, why do they go from liquid to gas like this? So to start off with, I want you to have a look at these three things. We've got a sparkler, sparkling away. We've got a cup of tea, and we've got a table. And I want you to think about which one is at the highest temperature, which one has got the most heat energy, and then what is the difference really between these two words, heat and temperature. So I'll give you a couple of minutes to think. You might want to just pause the video, jot down an answer or something, and then we'll go through it. Okay, so which one's at the highest temperature? Well, it's probably fairly obvious, isn't it? The sparkler. The sparkler is sparkling away, and these are probably at thousands of degrees, maybe 1,000 degrees or something like that. So iron filings actually, though it's really, really hot and sparkling away, and very, very, very high temperature. We've got a cup of tea. This cup of tea may be about, I don't know, what's 80 degrees if it's just been made, maybe 70 degrees, something like that. And a table, let's say it's in a room, so that it'd be room temperature, about 20 degrees. So this is definitely the hottest. But which one of these has got the most heat energy? So this is the hottest, but by what do we mean by heat energy? So heat energy is really what we're talking about is the amount of energy, the vibrations of all of the particles, or the movement of the particles. Now, if I just look at one little sparkle, one individual little sparkle, and one of these little iron filings, then although it'd be really, really hot and moving really fast, the particles be moving really fast in it, because it's only one particle, it wouldn't have that much energy. A cup of tea, although it's hotter than the table, again, a cup of tea is fairly small. A table would have lots and lots more particles than a cup of tea or an individual sparkle off a sparkler. So although this is going to be the coolest, it's not going to have as much temperature, it's going to have the most heat energy. And that's what we're going to look at over the course of this lesson really. What is the difference between temperature and heat, and what do we mean by those things? So just to make sure that you have been listening, we've got a cup of tea, fairly lukewarm cup of tea, and we've got a sort of a normal sort of temperature bath, maybe actually quite a hot bath at 45 degrees. So they're both at the same temperature. Which one's got the most heat energy though, and why? Have a little think. Okay, so yeah, it's the bath, isn't it? So the bath, they're both at the same temperature, so the particles in here, in these liquids, both can be moving around at the same speeds, got the same amount of kinetic energy individually, these particles, but there's just so many more particles here, so it's got a lot more heat energy because there's just so many more particles in the bath. Okay, so let's start being a little bit more specific with the words that we're using. We've said we're going to be talking about latent heat and internal energy. So let's start using these words really specific. Okay, so in the last video we looked at this heating curve, and we described how some ice, when it was heated up, should go along in this curve, and it would change from being some ice cubes at this point here to some liquid here, and change to vapor at that portion there. So if I was to heat up some ice cubes, then the ice cubes would change from a solid to a liquid to a gas. Okay, so we described that as you're adding energy constantly from this Bunsen burner, but as you're adding that, the temperature doesn't just rise constantly like as you might expect. It goes through these stages where the temperature doesn't increase, and that's because we've got to do something. We've got to change the state of this object. So we've got to change the state from solid to liquid, and then we've got to change the state from liquid to gas to do that. So let's remind ourselves of what a solid, a liquid and a gas look like. So if we were to draw a solid, a liquid and a gas, we might draw a diagram that looks something like that, wouldn't we? So solid, liquid, gas. Okay, and we've talked about the change in energy. We've talked about the fact that as we change from solid to gas, these particles here have got more kinetic energy. These have got slightly less kinetic energy, and these got even less kinetic energy. So the kinetic energy of these particles increases as it changes from solid to liquid to gas. And so if we go back to our graph, this ice here, the particles are in here are solid. So the particles are making up a solid, and so the particles have got a small amount of kinetic energy. When we go to being a liquid, the particles have got more kinetic energy, and then when we go to being a gas, the particles have got more kinetic energy. And that's really what we mean by temperature. So the temperature is a measure of this average kinetic energy. So the kinetic energy, if I increase the temperature, if I heat up my beaker with the ice in it, then what will happen is the particles will get more and more energy, and that energy will be kinetic energy, and so the particles will be moving faster and faster. When they change state and they change to being a liquid, I again heat up the particles, and the particles move faster and faster and faster. And again, when they get to being a gas, they move faster and faster and faster, but they've got to go through these changes between a solid and a liquid and a liquid and a gas. And so in this material in here, let's say this is water, we call this the internal energy of the water. The internal energy is made up of the kinetic energy, but also the internal energy is made up of the kinetic energy and the potential energy. Okay, and it's the total amount. So this is the total amount of the kinetic energy of all of the particles in here, plus all of the particles' potential energy as well. So we've described what the kinetic energy is. The kinetic energy is the amount of energy the particles have because of how fast they're vibrating or moving around in the different state that they've got. The potential energy is to do with the particles and where they are, really. So if you look at the particles, the difference between the particles in a solid, a liquid and a gas, the particles are very close together in a solid. In a liquid, the particles are slightly spaced, and in a gas, the particles are far apart. So to change from a solid to a liquid, what we've got to do is we've got to move these particles apart. And to change from a liquid to a gas, we've got to move these particles apart. And that's what we're doing really when we're looking at potential energy. So if you think of particles in a solid close together, and I heat them up. As I heat them up, you probably know that when you heat up a solid, it expands. And that's because the particles move further apart. But the particles are still bonded together. So I've drawn it like this sort of jaggedy line, almost like a spring. And if I heat it up even more, then this bond between them gets stretched out even more, and you can imagine a spring getting stretched out further and further. And that's really what we're looking at when we're looking at the potential energy. the further apart these particles move, the more energy they've got stored in this bond that can kind of snap back together, kind of like a spring. So the potential energy is because of the distance between these particles as they go further and further apart. Okay, so as I heat up some ice, to start off with, the particles move faster and faster and faster, and the temperature rises, the kinetic energy rises. But then we get to this point here where we know that it's melting. So the ice is melting, and at this point here, the potential energy is increasing. The particles are getting further and further apart until the particles' bonds are basically almost broken. They're very, very weak bonds. So the particles' bonds in a liquid are very, very weak. And then if we stretch those bonds even further, so we're a liquid, the bonds are very, very weak. If we stretch those particles apart even further, then the bonds would break. And that's really what we've got with the gas. The bonds are broken between the particles, and so the particles have gone from something where they're close together to something where they're far apart. And so we've been, when we've boiled it here, we've increased the potential energy again, stretched them further and further apart, and so that's why they've changed from a liquid into a gas. And so this internal energy is the sum of the kinetic energy plus the potential energy. Okay, so as I just said, the internal energy of a substance it's the sum of the kinetic energy of the individual particles that are moving relative to each other, plus the potential energy that the individual particles have because of their positions relative to each other. So it's adding both of these things up together that makes up the internal energy. So we've seen this graph, this heating curve, and we've talked about the sum of the kinetic energy and the potential energy being the internal energy. And this energy, when we're changing from a solid to a liquid, is kind of hidden. And one word we can use for something that's hidden is latent. So we talk about this latent heat. This latent heat is the heat that we've got to add to this solid to change it into a liquid. And when I want to change the liquid into a gas, the heat that I've got to give it is kind of hidden because the temperature is not changing. So this latent heat of changing this liquid into a gas, again, is the latent heat of vaporization. And so when we're talking about the specific latent heat, the specific latent heat is just for a specific amount. So latent means hidden. Heat is obviously the heat energy, how much energy I'm putting in, and the specific bit just means that I'm talking about a specific amount. So the specific in this case talks about 1 kilogram. So when I'm talking about specific latent heat, I'm talking about the amount of energy in this line here that I've got to add to 1 kilogram of this object to change it from a solid to a liquid. And when I'm talking about the specific latent heat of vaporization, is how much energy along this line here I've got to add to change it from a liquid to a gas. Okay, so the specific latent heat of fusion of a substance is the amount of heat required to convert a unit mass, so 1 kilogram, of the solid into the liquid without a change in temperature. And the specific latent heat of vaporization is the amount of heat required to convert a unit mass, again, say 1 kilogram, of a liquid into the vapor without a change in temperature. So for both of those cases, we can use this equation here. So the specific latent heat is the energy required to change the state of a substance. and we can use this equation here. So this is energy, and energy is measured in joules. This is mass, and mass is measured in kilograms. And then L is the specific latent heat in joules per kilogram. So we have this equation: energy equals mass times specific latent heat. And you need to be able to use this equation as it is. You also need to be able to rearrange the equation to find mass equals energy over specific latent heat, or specific latent heat. So this is an L. I know it might look like an I. This is an L. It's E equals mL. So the specific latent heat, and that would equal the energy over the mass as well. So you've got to be able to use it and rearrange it. Okay, so we are pretty much there. We've done our lesson on internal energy and specific latent heat. And you should be able to now state what internal energy is. You should be able to describe the behaviour of particles in solids, liquids and gases, and be able to describe what specific latent heat is, and also know the equation. And ultimately, like we said at the beginning, when you heat things up, why do they sometimes get hotter but sometimes change state? You should be able to answer that question as well. Right, well that's that lesson. Thank you very much. I've been Mr. Baker, and I will see you next time.